Okay, good morning, everyone. Today, we're going to talk about the next topic in the class, which is digital modulation. Digital modulation is let's say, the analog, if you will, to analog modulation. Remember, the difference between analog and digital has to do with how we represent information, right? So in the first half of the class, we were talking about analog modulation, where information is represented in a property of the analog transmit signal. And then we looked at the bridge from analog to digital, which was PCM and quantization. And now we're going to talk about digital systems. And in the context of digital systems, we're going to talk about three topics: digital modulation, source coding, and channel coding. All right, so everyone with me? What we're going to do, let's see if everybody is with me. If I ask you a question, it'd be great if I could just get maybe a hand wave, right? Because it's difficult to get feedback here. If you if you want to speak and say, yep, everything's good, that's fine as well. Okay. All right. So in terms of digital systems and digital modulation, as I mentioned, we start with the PCM waveform, right? So we've taken the analog signal, because when we receive a signal, we're going to receive an analog signal. Sorry. When we transmit the signal, we're going to transmit an analog signal, but the information in the analog signal will be represented in a digital way, right? And so we start with the PCM waveform. Now, when we talked about PCM and we talked about the bandwidth of PCM, we looked at it from a baseband viewpoint. But transmitting baseband pulses is not efficient. And so for the same reason that for analog systems, we talked about modulating to a carrier, those same reasons apply here. So transmitting at baseband is not efficient, because you need large antennas and you have significant power at low frequencies. So why don't we want to? So let me see if I can. I tried to set this up so I could do some writing. So transmitting baseband pulses is not efficient. Okay, you need to have large antennas, significant power at low frequencies. Now, for wireline channels, this is fine. Okay, because we don't necessarily have the constraint of bandwidth and power, but it's not good for wireless channels. Okay, well, one of the reasons that we saw before when we talked about modulating to a carrier was we wanted to allow multiple transmissions to happen simultaneously, because the wireless channel is broadcast in nature. Different signals can interfere with each other, right? So the solution is to modulate to a carrier, right? It's the same solution that we looked at when we did analog modulation. For digital modulation, we also modulate the transmit signal onto RF carrier at a certain center frequency FC. Now, when we discuss analog modulation, so we're going to see a lot of analogies between analog and digital modulation. All right. So if you think back to analog modulation, we could embed information in the amplitude of the carrier, in the frequency of the carrier, or in the phase of the carrier. So similarly, in digital modulation, we can embed information in the amplitude, frequency, or phase of the carrier. But remember, the difference is that the information representation is digital. Okay, so just as a quick sort of introduction to digital modulation, I'm going to talk about I'm going to introduce you to three binary digital modulation schemes. Okay, amplitude shift keying, frequency shift keying, and phase shift keying. All right, give me a second. Yeah, just. Guys, if you don't mind, just give me 1 minute, please. Okay, we're back. So as I noted, I'm going to talk about three of these digital modulation schemes here. Okay, amplitude shift keying, frequency shift keying, and phase shift keying. All right. All right. So as I noted, we'll start with the PCM waveform. So here's a polar non-return to zero PCM waveform. Remember, polar means that we're going to represent plus a 0 and 1 by minus and plus 5 volts respectively. And the non-return to zero means that in a symbol interval, we don't return to zero. Okay, so ASK, amplitude shift keying, is just basically you are going to modulate the amplitude. So here's my carrier, right? The carrier is cos 2 pi FCT, and we're going to just take my signal, my PCM signal here, and we're going to just put it in the amplitude of the carrier, right? So what this essentially means is that when the signal is +1, I'm going to send the carrier. When the signal is -1, it can, 1 plus d of t is 0, so you get 0. So essentially, when it's 0, you don't transmit anything. So this is called also called on-off keying, right? So when you have a +1, you send the carrier. When you don't have a +1, you don't. When you have a 0, you don't send anything. So that's amplitude shift keying. Frequency shift keying is shown here. Here again, just like when we talked about FM, in frequency shift keying, we'll change the frequency. So when you have a symbol 0, we'll send, so symbol 0, you send cos 2 pi f1t. For symbol 1, you send cos 2 pi f2t, right? So again, it's the discrete version of FM. The third one is phase shift keying, and here we're going to embed information in the phase. And here, the carrier, we're going to change the phase of the carrier. Now, here we only have two phases because there's two symbols, 0 and 1. So that's like, and two possible phases are 0 degrees and 180 degrees. But 180 degrees is just a flip of the sign, SIGN, right? So that's why I could take DFT and just put it right here in the as a pre-multiplying factor. So when it's a +1, I send cos 2 pi FCT. When it's a -1, I send minus cos 2 pi FCT. So is that clear? So this is just a first introduction to draw the analogy between analog modulation schemes and digital modulation schemes. So if you guys are with me, can I get a show of hands, please? Okay, so here's a diagram that shows graphically what ASK, FSK, and PSK look like, right? So you notice I told you ASK is like on-off keying, right? So this was, okay, so on-off keying, then, right? So so this is a 0, and this is a 1. Then we had FSK, where you can see that the frequency is changing. So this is, for example, frequency 2, and this is frequency, let's say F1. Okay, and then we have PSK, where exactly where I've drawn it here. You have a phase change or a sign flip. Okay. 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 So now we get into we're going to talk about a really important topic. okay, which is called signal space analysis. Now, the reason that signal space analysis is important is it allows us to represent the transmit signals in a geometric fashion. Okay, so it allows us to do geometric representation of signals. So remember that all communication systems transmit analog signals. We already know that, right? Even digital systems, right? The digital, in the digital system refers to how information is represented. And a digital system, we represent things as ones and zeros, right? And in digital modulation, if you remember the PCM model, the bridge from analog to digital, you can take the analog signal, sample, quantize it, generate a bit stream, right? And then the digital modulation part is to represent that bit stream, right? So digital modulation is to represent that bit stream by a transmit waveform, right? And that transmit waveform is the one that's shown here. Okay, it can come from a set. So I have a bit stream, I have a set of transmit waveforms. So this is my possible transmit signals. Okay, and the idea is that we can take a chunk of signals, like k bits, so k bits of the input, and we're going to map k bits of the input to an element of S. So look at the following example. Okay, so let's say we are going to look at pairs of bits. So if I get if my bits to be transmitted is 0, 0, then I'm going to send this signal S1 of t. If my transmit pattern that I want to send is 0, 1, I'm going to send this signal S2 of t. If it's 1, 0, I'm going to send S3 of t. And if it's 1, 1, I'm going to send S4 of t. Right? So we're mapping pairs of bits to transmit waveforms. Then my actual transmit signal, okay, could look something like this. Right? So for example, if I have a 0, 0, then I'm going to send this, right? Then if I have a 1, 1, I'm going to send this. If now I'm going to have another, let's say another, okay, this actually should be what? Should be 0, 1, right? Right? And maybe this one is, well, let me see. Let's go back a bit. Okay, if I can erase this stuff here. Okay, I'm going to erase this. Okay, let's start over. Okay, it might be easier. I think maybe so let's say that my symbol intervals are here. Okay, so these are my symbol intervals. Okay, now in this first symbol interval, I'm sending this, right? So this was 0, 0. Here, I'm sending this. This was transmitted because I wanted to send a 0, 1. This one is 1, 1, and this one is 0, 1. Actually, so there was another mistake there, right? This thing should be what? 1, 0. Yeah. Okay. So if this happened to be my bit stream 0, 0, 1, 0, 1, 1, 0, 1, then the transmit. So if this is my bit stream, okay, then this is my transmit. This is not capturing. Then this is my transmit signal. Okay, so this is what we mean that we are going to represent. That we're going to have a geometric representation of signals. We're going to be able to write things. right? So eventually my transmit signals is basically going to be a combination of these waveforms. Okay, and so we're going to reduce digital modulation to a study of how we combine these waveforms. Okay, let's okay, so we'll say a little bit more about them. We're going to represent signals, my transmit signals, as projections, okay, onto a set of basis functions. Okay, and just to close the loop here, for example, these four here could be the basis functions, S1, S2, S3, S4, and we see that any transmit waveform can be written as a combination of these guys here. Okay, so by doing this, by doing signal space representation, we get a one-to-one correspondence between a set of transmit signals and their vector representation, right? In the sense that we see that this transmit signal here contains, you know, sort of one of these signals here, one of these signals, and so on. So we'll see that in a more detail later. Okay, so why do we want to do this? The primary reason that we do this is that this simplifies the analysis and design of the communication system. Okay, it gives you simpler analysis and simpler design of demodulation algorithms. So that's what what we're going to study. Okay, we're going to study this exact thing. Okay, let me see. If you guys just give me one moment, let me check on something. Oh, I think we're okay. Sorry about that. I think we're okay. So just go here. Okay. So now for a short time, I'm going to need to do a little bit of math. Okay, so kind of bear with me. If there are any questions, please ask. This is really your shot to ask questions. That's why I set up these Zoom sessions, and I didn't just release material to you. So if you have questions, please ask. Okay. So we're going to start off with the notion of a basis set. So as I mentioned, we're going to write our transmit waveforms as we're going to represent them in terms of something called a basis set. Okay, so I need to define what we mean by basis set. So a basis set is here's a very deep result from math, specifically from linear algebra, which says that any m real energy signals, here S1 to Sm, can be represented as a linear combination of n less than or equal to m real orthonormal basis functions, phi1 through phi n. So let's look at that. So here I have m. Don't know why my iPad doesn't seem to be capturing stuff properly. So I want to say we have m signals, okay, and we have n basis functions, okay, right? So we have m signals here and n basis functions here, and what this result is saying is that you can always represent these m signals as a linear combination of these n signals, where n is less than or equal to m, meaning you never need more than m. So no matter how rich your transmit waveforms are, you need at most m basis functions. So here's what we mean by, so I mentioned this idea of linear combination, right? So this linear combination is shown here. Okay, so what we mean is that for every signal Si here, right, from this set, every Si, okay, can be written as the sum of a bunch of my basis functions here multiplied by some weighting factor here. Okay, so this is what we call a linear combination or a weighted sum. Okay, so what this means is that if you understand how to process the basis functions, you can understand how to process any of my transmit waveforms. Does that make sense? Is everybody with me? So we have a set of transmit waveforms, S1 through SM, and rather than trying to understand how to process them, we are going to represent them in terms of basis functions. Okay, so yeah, and then I mentioned that these basis functions are orthonormal. Orthonormal means orthogonal, okay, and unit energy. Basically, orthonormal means this. Okay, so this is orthonormal. Okay, it says that the integral of over one period of phi I, phi j is 0 if I not equal to j, and is 1 only if I equals j. Okay, so this is going to be a very, very important property of the basis functions. Okay, let's take a moment here. Let's take a step back. And please let me know if there are any questions. Are there any questions? Okay, so Sean says okay. How about from the rest of you? Can I get a show of hands? Yes, I understand this is a little bit mathematical, but you know, this in digital communications, you can't get away from the math because it really simplifies the analysis of the communication system. So for the folks who are here, can I get a show of hands? Are you with me? Okay, great. Thank you, Faith and Xiaofan and a few other people. Good. Okay, so somebody says, do we have to generate or find a set, or is there a starting point to find? So that's a good question, Shuni. So we generally have to find the set S. Okay, my set of transmit waveforms, in some sense, will define my digital modulation scheme. Oops, sorry about that. I lost that. Bring that back. Okay, so Shuni, the set S is something that we have to find because that will define my digital modulation scheme. Now, once you have the set S, finding the basis set is procedural. Okay, there's a way to find. Often you can look at S and find the basis set, or there's actually an algorithm to find this. Okay, and we'll discuss that a bit later. But does that answer your question?
Yeah.
Okay.
You
Great.
have answered that part. Thanks.
Okay, great. Let me see. I'm just trying to check on something here. So the algorithm for finding the basis set given the set S is called Gram-Schmidt. So the algorithm is called Gram. Okay, and this is Ashuni or anyone interested, in case you want to look this up. This is an algorithm for given a set S, this is an algorithm to find a basis set. Now, before we move on, let me try to give you a little bit more intuition why this idea of basis set is quite natural. If you look in, for example, in three-dimensional space, right? You can have, okay, see if in your mind you can imagine 3D space. So imagine you have an origin, okay, and then you have the many quadrants, right? Okay, and imagine arbitrary vectors in three-dimensional space, right? Now we want to, since every point in 3D space can be represented by a triple, right? If I tell you it's x coordinate, y coordinate, and z coordinate, you can tell me what the point is, right? That specifies a point precisely. Now, so let's say I'm looking at now imagine also in this 3D space you have you have unit vectors on the three coordinate axes. So in the x direction you have a unit vector, call it call it A. You have a unit vector in the direction of the y-axis, call it B, and you have a unit vector in the direction of the z-axis, call it C. Now, do you agree that every vector in 3D space can be written as a linear combination of A, B, and C? What do people think? Can every point in 3D space be written as a linear combination of A, B, C?
Yes.
Yeah, yes, we can, right? Because these are the three coordinates. So the unit vectors A, B, and C are a basis set for 3D space. I could have 100 vectors in my set, in 100 3D vectors, but the basis set is of size 3. And every 3D vector can be written as a linear combination of the three unit vectors, the three coordinate unit vectors, A, B, C. Okay? What we are doing here is we are generalizing that to functions. We are saying that any set of functions, so in this case set S, which has m functions, can be written as a linear combination of n basis functions. Okay, so if that analogy helps, you can use that. Okay, in fact, it's not if it helps. This analogy is exactly the right analogy. But because what we are doing is we're taking the digital communications problem, which has to do with analog waveforms, right? S1, S2, up to SM are analog waveforms, right? What we are doing is we are converting that problem into a problem in coordinate space, because when we represent the signal in terms of its basis function, all that really matters is this multiplying factor in front. This multiplying factor in front, Sij, is just a coordinate. Yeah, so it's just a coordinate of Si. So Sij is the coordinate of Si in the jth dimension. So yes, somebody asked, the basis functions is like x, y, and z unit vectors. That's exactly right. The basis functions are exactly your coordinate vectors. So I'm going to be able to write. Now, the beauty of this, right, is that later we're only going to have to worry about this. So we're going to be able to draw points. Instead of drawing analog signals, we'll be able to just draw points in an n-dimensional space. That's why this approach simplifies things. By the way, this representation into the basis set is sometimes called projection. Okay, you remember on the previous slide, I said something about by representing signals as projections, right? It simplifies things. Well, that's exactly what we are trying to do here when we represent that as a linear combination. Okay, so let's go on. I'll do some examples and things should become clear. All right, so let's look at just linear passband, where by linear passband, all I mean is that I have a carrier frequency. I have a carrier at some center frequency FC. So my carrier is AC cos 2 pi FCT. And I'm going to send, okay, I'm going to send information in either cosine or sine, which is just a phase shifted cosine, right? So this is essentially like I'm sending information in the phase of which signal I send, right? So now sine and cosine are orthogonal, right? Because the integral, they're orthogonal, meaning that the integral of sine times cosine over one period equals 0, right? So this is good. So sine and cosine have the potential to form a basis set. So we know that they're orthogonal because of this, and because of the scaling factor, the integral of cos, of phi 1 squared will be 1, and the integral of phi 2 squared will be 1. So they're also normal. So phi 1 and phi 2 actually can form an orthonormal basis set. Now, what we're going to do is we can say, okay, since I now have a pretty nice basis set, sine and cosine, I'm going to use that to build new transmit waveforms. So for example, so if I define phi 1 and phi 2 on some symbol interval, so let's say my symbol interval is t. So in 0 to t, I define phi 1 and phi 2. Okay, then I can start to generate signals Si with as linear combinations of phi 1 and phi 2, where in this case here, my multiplying factors Si1 and Si2 are just real numbers. Okay, now, yeah, so does that make sense? So this gives you an example of a set of transmit waveforms here, Si, that is representable by two basis functions, sine and cosine. Okay, now a little bit about notation. Because for example, S1 can be written as S11 phi 1 plus S12 phi 2, and phi 1 and phi 2 are kind of like standard, they're agreed upon by everyone. The only thing that defines S1 is S11 and S12, right? And this is just a vector in 2D space. I'm going to call that S1. So this underbar here, S1 underbar, depicts or denotes a vector. Okay, S2 is representable by its coefficients, S21 and S22, and we call this the signal space representation, right? So what we've done is we've taken this analog signal here. So remember, this right here is an analog signal, and we've taken it and we represented it by a point in 2D space. Okay, and we can even plot that point in 2D space. Here's S1 and here's S2. And what we're going to find is that this geometric view of S1 and S2 is going to be very useful for us. Okay, so in this simple example, do we see at least what signal space representation is all about? We're going to see later why this is useful, but right now I want you to understand what it is in this example. So can I get a show of hands? Is everybody with me so far? Yeah, okay, great. Okay, if you have a question, please feel free to ask it now. You can just unmute yourself and ask, or you can type your question in the chat window. Okay, all right, so we got that. Here's another example. So this was what I call linear passband. So I'm sending at a fixed frequency and sending information in the sine and cosine. Okay, let's look at another example called binary phase shift keying. Okay, in binary phase shift keying, I'm either going to send a plus cosine or a minus cosine. Okay, but I'm going to write this out kind of in a little bit more detail. So the binary part of it, okay, says I have two phases. Okay, the two phases are going to be 0 and 180 degrees. right? So my transmit waveforms look like this, okay? So I have S0 and S1, okay? S0, so since when n is 0, we get a pi degree phase shift. When S is 1, I get a 0 degree phase shift. So we see that, right? And we know that a pi, sorry, not pi degrees, pi radians. Sorry about that. A pi radian phase shift, which is 180 degrees. And we know a pi radian phase shift is just a sign flip. So actually my transmit signals are plus cosine minus cosine, okay? But I can write it in sort of slightly more general terms as shown here. Then if I have a symbol duration, again, my symbol duration will be 0 to t. I have two phases, 0 and pi, and the two transmit signals look like this, okay? The basis set, so in this case, what's the size of my basis set? So I have two transmit waveforms, S0 and S1, so these are my transmit waveforms. What's the size of my basis set? Can anybody tell me? How many basis functions do I need here? I need just one, because I'm transmitting cosine or minus cosine. The only thing that changed was the multiplying factor in front, right? So this tells you that my basis set is just cos 2 pi f ct. Now this scaling factor is there to make the basis function have unit energy, okay? Then S0 of t, so remember Sn was written here, and again this was also, I chose the scaling thing here so that the transmit waveform has energy EB. Okay, it was just because like later when we compute signal to noise ratio, it would be useful for us to have an EB. Okay, but if I look at my transmit transmit waveforms here, and I look at the basis set here, we can write S0 and S1 in terms of the basis set as shown here. Okay, S0 is just minus square root of EB phi, and S1 is plus square root of EB phi. And so it's the coefficient in front of here that matters. Okay, and I can take this and I can plot them on a signal constellation diagram. So this we'll see a lot. This is the constellation or signal constellation diagram of binary phase shift keying. We often use binary phase shift keying as an example because one, it's a very simple strategy, and it's a strategy that can be generalized into strategies that are used in communication systems. Okay, so everyone with me here? So this is sending information in the cosine. Okay, and we have one basis function. If I want to do binary phase shift keying, my signal constellation looks like this. All right, so we now have two examples: linear passband and binary phase shift keying. Any questions? So now is a good time to ask questions, because what I'm going to do now is I'm going to show you the power of the geometric representation. So the next slide, slide 9, what we're going to do is we're not going to have equations anymore. We are just going to draw signal constellation diagrams. And because we're just drawing signal constellation diagrams, we can view things geometrically, or we can view things pictorially, but each of these represents a modulation scheme that if you try to write down the equations, it'd be very messy. Okay, so let's start with that. So we're going to start with the first one, which is binary phase shift keying. We know that the signal constellation of binary phase shift keying is, well, it's two. So binary phase shift keying is two phases. It's phase shift keying with two phases. So we can sometimes call it 2 PSK. So there's two constellation points here, and we see that they are opposite from each other. We have two different phases. Now, we'll see that when we want to decode, we need to separate these two phases. So it's good to have the two phases or the 2 points as far apart from each other as possible. right? This is why, for example, this constellation point is better than, for example, if I was to do this. This is also a possible 2 PSK constellation. So the question is this good? Who can tell me? Who can tell me how good this is? Okay, so I'm having a little problem with my, let me see. So the question I want to ask you is that good? Interesting, I can't do a dot. Okay, so can I get a show of hands? Is this good? A yes or no?
No.
Yeah, someone said no. Anyone else? Can I get maybe the rest of you involved? Okay, there are a couple of questions. Some people saying no. Sean, you said depends. Why is this good? Like, what does it depend upon? Sean, would you like to share? Phase is the same, but amplitude. Phase is the same, but amplitude is not the same. That's a good point. The amplitude is different, so this is not really. So that's a very good point, Sean. This is not really phase shift keying. Maybe I should let's redraw this. So this is a good point. So my point was that this is not good because these points are very close to each other, and it's going to be hard to tell them apart. Let's do this. Let's erase this. And let's draw a new one. Okay, so Sean, now you tell me. Here's this. I'm gonna make these two. I'm gonna change the phase to be different, but they're closer to each other. So now, Sean, is this one better than the original one? Jihao, I'll get to your question in a second, and Shunyi as well. So Sean, let's close the loop with you. Is this a constellation better than the original constellation I drew? Yeah, there's a phase change of 180 degrees, Sean. You're correct. But what we'll see later, and I don't expect you to see it now, but the 2 points are closer to each other, so it becomes harder to tell them apart when there's noise. Because remember, noise is going to push these guys around. So we'll see that later. Maybe it's not worth discussing it now, but intuitively, I want you to see that you need to push these points as far apart as possible. Okay, Shunyi asked, is there even an application of such a scheme? Absolutely. Yes, binary phase shift keying and its generalization. For example, in the next diagram, I draw something called quadrature phase shift keying of 4 PSK. And 4 PSK and 8 PSK and strategies like that are actually modulation schemes that are used in practice. Shunyi, does that answer your question, or did you have a specific reason for asking if there's an application?
I was actually asking more of what happens when the bits are on the same side of the diagram.
Oh, right, yeah, absolutely. Yeah, you're right. When they're on the same side, it's not very useful. You're absolutely right. Jihao asked, what does the axis mean in this diagram? Okay, Jihao, so the axis here, you're talking about this axis, right? Or do you mean the x's? Yeah, so the two axes are the coordinates in the basis functions. So in this example, for BPSK, there was one basis function. So that's why these points lie on one axis. So for BPSK, there's one basis function. If you had two basis functions, so let's go to the next example, which is QPSK or 4PSK. In this, there are two basis functions. Now, it turns out that the two basis functions here are just sine and cosine. Okay? But as I said, that doesn't matter to us right now. If I have two basis functions and I And as long as they're orthogonal, then this axis is the coordinate of basis function 1, and this axis is the coordinate of basis function 2. And these 4 points, if you look at the coordinates of these 4 points, they tell you what the, how much of each basis function they contain. So does that help to explain? Yes, the coefficient of the sine and cosine, that's correct. Okay, so now a BPSK, there's 2 constellation points, so I get 1 bit per symbol. QPSK has 4 constellation points, so I get 2 bits per symbol. That means to map to a QPSK point or 4 PSK point, I have to have 2 bits. So 2 bits come in, and I'm going to map that to one of these 4 constellation points. So for example, it might be that this is 0, 0, 0, 1, 1, 0, and 1, 1. Okay? Let me see. Let me fix that. This is 1, 1. Okay? Now, to give you an example of another QPSK constellation, I can look at this diagram here. So this is another BPSK constellation. Okay? Kaihua asks, so a pair of so it's not basic functions, it's basis, but that's okay. So a pair of basis functions is always just 180-degree difference. No, it's not the case. Okay, like that might be a good thing in many situations. For example, in BPSK, like so sine and cosine are not 180-degree phase shifted, right? Sine and cosine are actually 90-degree phase shifted, right? Or pi over 2 radians. Okay, what you're trying to say is that the constellation points are 180-degree phase shifted. And so for BPSK, that is the case, but you notice for QPSK, it's not. The constellation point corresponding, this one corresponding to 0, 1 is 90 degrees away from the one corresponding to 0, 0. Okay? Kaihua, does that help? Okay, good. So now the second diagram for 4 PSK, I've given you 2 examples here of 4 PSK. Now, BPSK and QPSK are used so much that they have their own names. Instead of 2 PSK and 4 PSK, we call them binary phase shift keying and quadrature phase shift keying. The quadrature stands for 4, but it's 4 PSK. Okay? Now, if I want to have 3 bits per symbol, then I can't use BPSK or QPSK, right? Because there's only 2 or 4 constellation points. If I want to have 3 bits per symbol, I need 8 constellation points. So if I want to do that via 8 PSK, then I need to have 8 points, right? And since I'm doing phase shift keying, right, these points must fall in a circle. Actually, if you look at BPSK, the 2 points fall in a circle, right? They're the same distance from the origin. The same thing for QPSK. Excuse me. The 4 points are the same distance from the origin, so the points fall on a circle. So 8 PSK easily generalizes that. So I'm going to find 8 points that sit on a circle centered at the origin, and that gives me 8 PSK. And I can, correspondingly get M PSK. I get M points centered on a circle. Now, since I want to maximize the distance between points, I'm going to make them uniformly spread around the circle. I'm not going to have them bunch around. Okay? Now, look at the beauty of this. For 8 PSK, if I have to write out the transmit waveforms, I have to write out 8 kind of complex transmit waveforms, right? Because, for example, this point here has, so for 8 PSK, the 2 axes are also sine and cosine, right? These are my 2 basis functions. In all the examples on slide 9 here, okay, on slide 9 here, for all the basis functions, sorry, for all the constellation schemes, there are two basis functions, and they are basically sine and cosine. Okay, this is that linear passband example. Okay, but if I want to write out so let's say I want to write out what this signal is, then I need to say, oh, I have some sine and some cosine. But on the diagram, it's just a point on the circle. So this graphical, sort of visual way of looking at it is going to simplify our understanding and analysis of digital communication systems. So the first three examples, BPSK, QPSK, and 8PSK, are phase shift keying strategies, in the sense that the only thing that differs between the different constellation points or transmit signals is the phase of the transmit signal. The amplitude is the same. So all the PSK are constant amplitude, but there's no reason why I cannot include amplitude into the picture. So the next example, the fourth example that I have here is called 16 QAM. QAM stands for quadrature amplitude modulation. What we're going to do in QAM is we're going to embed information in amplitude as well as in phase. So here's the constellation diagram of 16 QAM. So because I'm saying it's 16 QAM, there's 16 points. So there's 4 bits per symbol, all right? And the 16 points are laid out like this, okay? So we see, for example, here is this point here could you know, S1 could represent S1. This is S2, S3, and this could be, let's say, S4. Okay, so this now QAM is actually a very popular digital modulation scheme. In fact, we don't use 16 QAM. We actually use like larger modulation strategies, like 64 QAM, okay, and 256 QAM, or 128 or 256 QAM. But 16 QAM is sort of easy to draw and visualize. Now, again, I want to point out, imagine, 256 QAM is used, yeah. Seachan asks, what is symbol? The X on the constellation. Yes, this X is my transmit symbol. It also represents the transmit waveform. Remember, this axis could be, for example, sine, and this axis could be cosine. And so when I send S1, it tells you how much of sine and how much of cosine. Now, in this case, since all the points have different distances from the origin, amplitude is coming into play, right? But since they're also at different angles, phase is coming into play. So QAM mixes phase and amplitude, and it's a very efficient scheme. Okay, Benjamin asks, so is the point to show how we map the number of bits we would like to transmit on the number of points on the constellation diagram, so we can represent them distinctively? Yeah, so right now, that's exactly right. Right now, I'm asking you to visualize transmit waveforms on this type of diagram. Later, what we're going to do is we're going to do constellation design by just designing constellation diagrams. We're going to do decoding by just imagining constellation points getting pushed around by noise. And so if constellation points get pushed around by noise from their original position, we'll be able to figure out how to decode them by, for example, finding the closest constellation point. Okay, so that's exactly right, Benjamin. We want to visualize this in a graphical way, and each of the points represents a transmit signal. But because of the signal space or the geometric representation, we can deal with points in the plane, okay, which is quite easy for us to visualize, and it's much less messy than writing out, in this case, 16 analog signals. Okay, everyone with me so far? Okay, Shuni has 2 questions. I see the QPSK scheme has a 0, 0, 0, 1, 1, 0, 0. What about the gray counter scheme? All right, this is an excellent point, Shuni. When I did the mapping for QPSK, I kind of was just using it as an example. But yes, you would normally try to do the mapping from bits to constellation points in a better way. What you'd want to do is to make sure that neighboring constellation points or constellation points that are close to each other don't differ in too many bits. So for example, if I had to redo this, so let's go back to the QPSK constellation. If this point remains as 0, 0, it's not a good idea to have this point be 1, 1. Maybe I want to make this point 1, 0. In which case, I need to change this to 1, 1, and this can remain at 0, 1. So Shunya, you're right. The benefit of the new way I did it is that now neighboring points, if you notice, if you compare these 2 points, they differ in only 1 bit. So if you make a mistake, if let's say I sent this, but somehow I decode to this, I only make 1 bit error. Shunya, does that answer your first question?
Yeah, it does.
Okay. Second question is 16 QAM has no points on the lines. Is there any application where some are on the axis? Yeah, absolutely. If you want to, you could rotate this. Yeah, just like we did here. If you look at the QPSK, I gave you 2 examples. One where they're on the coordinate axes, and one where it's offset. Okay, so the design, like whether you choose the standard QPSK that's on the left or the offset QPSK on the right is a design decision, and there's advantages to either one. The same exact thing holds true for QAM. If you want to, you can rotate this.
So that means in a way it's all just spaceship.
Yeah, exactly. Yeah, and that's the beauty of it. When you look at this in this diagram, phase shift of the entire constellation has no effect, right? In fact, if you can synchronize to the phase shift, you can undo it, right?
Yeah.
And that's exactly synchronization. If you think back to when we talked about synchronization in phase lock loop, right? You can use a phase lock loop to do phase synchronization as well, right? And then undo it. If every point is undergoing the same exact phase shift, you can just undo it. You can learn it and undo it, right? So if your channel introduces a phase shift, you can undo it by using a phase lock loop. Okay, Sean asked a good question. What's the pros and cons of 16 QAM as compared to 8 PSK? Yeah, so the good thing, yeah, so you're correct. 8 PSK has 3 bits per symbol, and 4 PSK has 4 bits per symbol. So that's one of the advantages of 16 QAM. But given a constant power, right? Meaning, so in this diagram, the power of a constellation or of a signal is its distance from the origin, right? So for the 8 PSK, you take you look at the distance of a point from the origin. So of course, 8 PSK, because it's constant amplitude, every symbol has constant power, and that's the power of the 8 PSK signal. Now for 16 QAM, you got to look at all the distances and kind of average them out. If every constellation point is equally likely, which is a good assumption, you can just take the average distance, right? And that will be the power of the 16 QAM constellation. But you're right, for a fixed average transmit power, the symbols in 16 QAM are closer to each other than, for example, QPSK, right? The advantage is that you get, let's not compare 8 PSK with 16 QAM. Let's just compare QPSK, which is also like QAM, right? Offset QPSK, actually, so QPSK is just 4 QAM, okay? So if you look at 4 PSK and 16 QAM, the advantage of 16 QAM over 4 PSK is more bits per symbol. The disadvantage is that the symbol error rate is going to be higher. So that's a very good point you make, Sean. But I'm going to tell you this: what's going to save us is channel coding. Okay, we're going to modulation is not used in isolation. Modulation is used along with channel coding, and channel coding has the property that I get robustness to noise. So the beauty of this is that by crunching things closer together in 16 cram, you get more bits per symbol, which is good, right? Because the power cost to you is per symbol. If you can crunch more bits into that symbol, that's good for you. That's more efficient, but you make more errors. But if you can do channel coding to help you become robust to those errors, you get a win-win situation. Sean, does that answer your question? Okay. Wensin asked, so meaning we can have points on axis. Yeah, you can if you want. You can design your constellation because now it's more visual and graphical, right? We're looking at it geometrically. You can design it how you want.
Oh, sorry, Prof. But if we have S2 and S3 on the horizontal axis, right, wouldn't it be like no difference?
Why? Can you explain what you mean?
Because like you said, 16 QAM, it depends on the amplitude and the phase. But if S2 and S3 is on the horizontal axis, right, then the amplitude and the phase would be the same, right?
No, the amplitude is different. The amplitude is the distance from the origin.
Oh, okay, thank you.
Yeah, okay, good. But you're right, when they're on the axis, they'll be the same phase. But actually, if you notice, S1 and S2 are already at the same phase, aren't they? Like you take a look at this. I draw a line this way. Aren't these 2 points at the same phase?
Oh, yes.
They're just a different amplitude. So what I'm saying is you can rotate this entire constellation so that if you want, you can have those two be on the axis. It doesn't change anything. That's actually the beauty of looking at it like this.
Oh, so the amplitude is from the origin of the.
Yeah, exactly. Origin is like zero power because remember the coefficient is in front. If you go back here, remember this coefficient here, right? Like look at S0. S0 has a coefficient in front, right? So that's the same. This square root of EB here is the same square root of EB on the constellation diagram. That's the distance from the origin, and that determines the power, right? Because if you look at S0, or S1, it's square root of 2b over t cos 2 pi fct. If you wanted to compute this power, you just take this, square it, and integrate it, right? Right, integrate it over some duration, take the average, and take the limit.
Okay.
So the distance from the origin is the pre-multiplying factor in front of the basis function and will determine your power. In this case, these signals on the diagonal have both a sine and cosine term, so you got to add both those up. You add the power in the sine and the power in the cosine. But that's equivalent to just taking the distance from the origin. Okay, I think what we'll do is we'll stop here. Okay, when we come back, we're going to talk more about, so when we come back next time, I'll review this and we'll talk about how we can use the signal space representation to understand and design digital communication systems.